we should not ignore lines. So we talk about the lines in a Cartesian plane. So lines, and there are different ways we can express lines in Cartesian plane. Okay, so the first thing is we have an xy plane and we have a simple line. Okay, and it has a point here, and this point is basically um, x y in terms of the coordinates, and it has projections on x-axis. Okay, x here and y here, and this point, let's put a cross here for the point, and we have certain aspects of lines. For example, this is the inclination angle alpha, and now we define is basically x1 y1 at the origin or in the beginning somewhere, can be at the origin, and x2 y2, the second point on the line, can be the final point of the line as well. Okay, and in case if the line is not passing through the origin, so what we have is, here you see what we have is the intercept, this intercept c, which is the y-intercept. So x1 y1 is the point here, and x2 y2 is the point there. Let's just put x2 y2, not the brackets. Okay, so the general form is ax plus bx plus c is equal to 0 in standard cases, and when we discuss the slope, it is basically defined depicted by m, and it is actually delta y by delta x, which means it is equal to y2 minus y1, y coordinates, yes, and x2 minus x1, yes. So this is the slope. This is the slope, and there is a form which is called, there are different forms. For example, the first simple form is slope intercept form, and this form is y is equal to mx plus c. Y is equal to the product of slope and the x coordinate plus the y intercept. Okay, so see, so this is what is happening here, and we can put some numbers and solve, but that can be done later as well. So what I'm trying to tell you here is that there are different versions. For example, there is a point slope form as well. So in this case, you must have the slope as well as the intercept. You put the values and you get the equation in terms of y and x. Okay, and now we have another version which is point slope form, which can be just established from this form of the slope. Yes, initial form of the slope, and I will tell you how. For example, point slope form is something like this: y minus y1 is equal to m into x minus x1. Okay, so what it means is basically we don't know y and x, but we know y1 and x1. Okay, and we can also graphically or somehow estimate, let's say, m, or we are given these values simply. So what we do is we plug in the values m, x1 and y1, and then we have a general form for the line equation. Yes, but this can basically be derived from the slope, and the slope says, in the equation 1 it says m is equal to y2 minus y1. You need 2 points, so you find the, say, the difference between the y coordinates and the x coordinates, which is y2 minus y1 by x2 minus x1. Okay, so once you have this, you can do something like this: y2 minus y1 is equal to m into x2 minus x1. Okay, this is something that we have. Okay, so let me just bifurcate here. So point slope form is when you have the slope and a point. Okay, and now we're looking back into the slope because we're trying to figure out a form from 2 points: y2 minus x2 y2 and x1 y1. So when we have the information of 2 points, so this is basically 2-point form. Yes, when you have information about 2 points, this is what you can establish. But how? So the second point, you okay, wait. So we make a little correction and try and avoid the confusion. So you see, this is interchangeable, but we still try and avoid confusion. So we do not discuss the points 2-point form yet, and we work with the point slope form. Okay, so the point slope form says that m is equal to delta y by delta x is equal to y2 minus y1 by x2 minus x1. Okay, this is what we have. And so in point slope form we have the information of 1 point in the slope. Okay, so for the second point we can put the general version, let's say y minus y1 and x minus x1. So the form becomes y minus y1 is equal to m into x minus x1. Okay, see, we have the slope and we have x1 y1 information for first point, and for the second point xy, uh, we use this form, the mathematical form. And then when we get to 2-point form, we once again use the slope, which is y2 minus y1 by x2 minus x1. So the trick here now is y2 minus y1 is equal to m into x2 minus x1. Okay, so the trick here is that so we use the value or the form of m from equation 2, So y2 minus y1 is equal to y minus y1 by x minus x1 dot x2 minus x1. Okay, so the form becomes x minus x1 by x2 minus x1, yes, equal to y minus y1 divided by y2 minus y1. So this is the 2-point form, yes. Or simply we can have y2 minus y1 by y minus y1 is equal to x2 minus x1 by x minus x1. Yes, so this is a 2-point form, but then this also implies that uh, y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. So this is the third form, the 2-point form. Alright, so this is the slope here. Let's call it a slope intercept form. Let's call it 1. And the point slope form, let's call it 2. Now we have the 2-point form, which is 3. Yes. So for better nomenclature, I change the sequence, the numbering. Rest is the same. So there's one more thing, which is a double intercept form, and for that we need to have this thing in mind: x, y, and the line with the intercept a on x-axis and b on y-axis, and this is the form. So x by a double intercept, it is not used frequently, but it can be required. So x by a plus y plus b is equal y plus y by b is equal to 1. So this is the double intercept form. Let's call it the form 4. And let's not number it. It's because we're not, it's there as it is, and we will not derive it today. So what we put alongside this is the relation for tangent theta in terms of slopes. So we have these two okay, let's just have some surface knowledge. M2 minus m1, which is slope 2 minus slope 1, divided by 1 minus 1 plus the product of m2 and m1. Okay, so this gives us the tangent of the angle in case of two lines. Okay, so for example, there are two lines and they have two slopes, L1, L2, L2, L1. So this has M1 and this has M2, and both are on the XY plane, something like this. It looks something like this. Yes, and they have these parameters. And there's one more situation wherein we are looking into the concurrency of lines. For example, there are three lines, L1, L2, L3, L3 with M3, L2 with M2, and L1 with M1 lines and their respective slopes. So the condition for concurrence would be something like this. I will show you. Okay, so the general form would be a1 aix plus biy plus ci z. Okay, and for line 1, let's say it would be a1x plus b2y plus a1y plus a1x plus b1y plus c1z. This is the equation for the first line, and for the second line, a2x plus b2y plus c3z. Okay, this is in the 3D space, not just x and y, but also let's say 3D space, which is not explained here, but this is very much possible. L3 is equal to a3x plus b3y plus c3z. So the condition for concurrence would be we form a matrix a1 b1 c1 a2 b2 c2 a3 b3 c3, and we take determinant, and this determinant should be equal to 0. So this is the condition for concurrence of lines, and this is the case for 3 lines here. It's also possible for 2 lines to check. So we now have the partial fractions. And we have basically 3 cases. Case 1 is something like this: 1 by x plus 1 into x plus 2. So how we open up this equation is the general version: a by x plus 1 plus b by x plus 2. These partial fractions are used in integration. So this is therefore the preliminary work. Okay, so case 2 says, let's call it 1 here. Case 2 says 1 by x plus 1 into x plus okay, 1 by x plus 1 whole square. Yes, this is case 2, and this opens up like this: a by x plus 1 plus b by x plus 1 whole square. So this is the second case, and we will discuss with expansion as much as possible, but for the current segment we will see how much is possible. Case 3, we have this version x plus 1 x square plus 1. Now notice the increasing degree of x, and x square plus 2 in a different term. So we open it up something like this. Yeah, so ax plus b by x square plus 1, the first term, then cx plus d by the second term, x square plus 2. Yes, so this is the general opening of the partial fractions. Okay, and so what we can do is we can solve for the first two cases, which are somewhat simple, and then see what happens. Yes, so we have this form. Let's say there is 1 by x plus 1 into x plus 2, and we are supposed to solve it. This is case 1 for partial fractions. So we open it like this: 1 by a by x plus 1 plus b by x plus 2. Okay, so we cross multiply. 1 is equal to a into x plus 2 plus b into x plus 1. Okay, we cross multiply and simplify, and then compare the coefficients in the end. So 1 is equal to ax plus 2a plus bx plus 2b. Okay, so 1 is equal to ax plus bx plus 2a 2 into a plus b. Yes, so for x, okay, wait, so we have this x here with the common factor a plus b, and then we have this a plus b with the common factor 2 as which is taken out. Okay, so we now compare the coefficients. So for x on the left side we have 0, so a plus b is equal to 0. This is equation 1. This gives us a is equal to minus b, and for 2a plus 2b, this we have on the other side 1. Okay, so now we can solve for a and b. So as a is equal to minus b, so minus 2b plus 2b is equal to 1. Wait, there's a mistake somewhere. So we have spotted a little mistake: bx plus b, which means here we have 2a plus b, and here we have also plus 2a plus b. Okay, so 2a plus b is equal to 1 on the other side. which means b minus 2b minus b is equal to 1, so b is equal to minus 1, so a is equal to 1. Yes, and now we can develop the form by back substitution in 1 here. Okay, so the form becomes equal to 1 by x plus 1 minus 1 by x plus 2, and now this version is very much integrable. We can integrate this without serious problems. Okay, so this is the aim for partial fractions basically. Okay, so we have a little bit of more work to do with partial fractions on the second case, and we will leave the third case for the next session. Okay, so for the second case, okay, we have this thing. Let's say 1 by x plus 1 whole square is equal to a by x plus 1 plus b by x plus 1 whole square. So this is an equation here now for the second case. Okay, and we cross multiply 1 by x plus 1 into x plus 1 is equal to a by x plus 1 plus b by x plus 1 into x plus 1. We open up and then cross multiply, so we expanded and now we're cross multiplying, so the situation becomes 1 is equal to a into x plus 1 plus b into 1, or yeah, which is b. Okay, so the situation is ax plus a plus b, and it is yes. So now if we compare coefficients for x, when we compare the coefficients, we have a is equal to 0, and for a plus b we have the constant 1 here. So a is equal to 0, and a plus b is equal to 1. So 0 plus b is equal to 1, so b is equal to 1. We do the back substitution in the equation 2 to get the final form, which is equal to 0 by x plus 1 plus 1 by x plus 1 whole square in the main equation here. Okay, so this is equal to 0 plus 1 by x plus 1 whole square, which is equal to 1 by x plus 1 whole square. Yes, so these are the examples of the basic cases of partial fractions. So we look into the mathematical induction. As our next topic. There's something wrong with the focus, and I hope it gets sorted without problems. Yes, so we have this case for mathematical induction. mathematical induction. We'll write shortly. So this is for establishing the sequence. For example, there is a sequence n into n plus 1 by 2, and we have a procedure to check and then establish a sequence. For example, so check it n is equal to 0, which gives us 0 into 0 plus 1 by 2 equal to 1 by 2. So it gives us a valid number to proceed. So we put n is equal to 1. So this becomes 1 into 1 plus 1 by 2, which is basically 2 by 2, which is 1. Yes. And now we put n is equal to k. So k into k plus 1 by 2. We can expand it. K square plus k by 2. Yes. And then we put n is equal to k plus 1. So k plus 1 now is equal to k into k plus 2 by 2 is equal to k square plus k plus 2 plus k square plus k plus 2 plus 2k. So it gives us k square plus 3k plus 2, basically divided by 2. K square plus 3k plus 2 divided by 2. Yes. So now we can safely say that let's call it 0th term and the first term and the kth term and then the term with the subscript k plus 1. Yes. So a0 is less than a1 is less than a k is less than a k plus 1. Okay, therefore we have a sequence. So we check with the induction if there is a sequence or not, of course for the numeric values in real numbers. So we do a little bit of inverse trigonometry. Inverse trigonometry, and for that we once again draw the triangle. Okay, so x here, y here, x square plus y square under the root. This is hypotenuse, this is perpendicular, this is base. Yes. So in this case we're given a function